All right, so I told somebody I was going to do a video of a short video of how to do the assignment today, but I got to thinking I really haven't given you guys much of a lecture or anything yet. So here we go. Let's talk about John Napier and logarithms. That's what we're looking at this week in week 4 on early modern problem solvers. First of all, John Napier, he's the inventor of logarithms. He was born in 1550 and died in 1617. He was the son of Sir Archibald Napier and Janet Bothwell. I believe this is, in terms of royalty, this sounds like a name that I'm familiar with. At least they were well off, I believe. John was the eighth Laird of Merchiston, and Merchiston is just an estate near Edinburgh. Actually, it's Edinburgh, if I say it correctly. He was the eighth one. The laird is just the owner of a large estate or a large plot of land. So he was the eighth guy that had this huge estate in Merchiston near Edinburgh. He graduated from St. Andrews in 1563. Notice he was 13 years old when he graduated from St. Andrews University. St. Andrews was built between 1410 and 1413. It was really built due to the warring factions of Catholics in a split papacy. We'll find that religion has a lot to do with the math and the science that came out of whatever era it happens to be. And St. Andrews is just one of those colleges where they said, hey, you know what? Let's ignore religion and just get some learning in here. Some famous people from St. Andrews. Edward Jenner, the guy who discovered the smallpox vaccine in 1792, graduated St. Andrews. Benjamin Franklin, a U.S. dude, has an honorable PhD from St. Andrews, so that's pretty impressive. And kind of a modern author, I guess, kind of not, since it's 100 years old. I guess it depends on your version of modern. I'm a mathematician. Modern is like the last 2,000 years. Rudyard Kipling also graduated from St. Andrews. Now, John was married twice. During that time, and guys were married. That's just the way it was. You're married, you have kids. If the wife dies, you get married again. So his first wife, he married in 1571 at the age of 21, was Elizabeth Stirling, a year after returning to Scotland after travel. So after he graduated from St. Andrews, he went traveling. This 13-year-old kid graduates, right? And he's probably 14 or 15 before he really started traveling Europe and far West Asia, just learning, just experiencing what it was like in different areas. He came back after a couple years, married Elizabeth Stirling, and they had 2 kids, and they lived at Gartner Castle. She died in 1579, so they only had 8 years together. He married Agnes Chisholm right away. They had 10 kids, and once John Napier died, Agnes went with the kids. They returned to Merchiston and lived there. I'm guessing it's still in the family. I didn't look that up. He was a Scottish Protestant. Now, there are major religious battles all over the world, but Scotland, just the whole UK area, Wales, Scotland, Ireland, I know they're not all the same, or they're not all in the UK, but that area of Europe, huge into religion. As a fervent Protestant, which means he like a Protestants. That's the English Christianity, I believe, following King Henry's lead when he established the Protestant Church. Because he was a Protestant, he really hated papist, people who were all aligned with the Pope. He hated atheists and anybody that was neutral. He thought you should have an opinion and be passionate about that opinion. He was such an inventor, and if he hadn't been so much into the church, they would have thought he was a warlock. There's actually people that had been prosecuted for being witches, wizards, warlocks, that sort of thing. And some of his inventions evidently were borderline not good for the church. That's not what I wanted. I wanted Scottish Protestant here. Let's see. After he was being a warlock, after he was accused of being a warlock, he wasn't being a warlock. I know my words, I promise. James IV of Scotland, the future James I of England, had written a book on demonology. And in this period, mathematicians were frequently suspected of being in league with powers of darkness. And I gotta tell you, most of my students in Math 1320, the only math class they have to take in order to get a college degree, they pretty much think I'm in league with the devil too. I'm just saying. At first, he called logarithms artificial numbers, so he didn't even believe that they existed. He later coined the term logarithm, which is number of the ratio. So that's all a logarithm is. It's a number of a ratio. Okay, so blank slate here. The original source that we're going to look at, and it's the one that your project this week is based on, it wasn't actually published, I don't believe, until after John died, or really towards the end of his life. And one of his sons, Robert, was actually a mathematician too, and he wrote a preface. In the preface, Robert reminds readers that his father had published a book on logarithms several years earlier, and in it he mentions that he would write another explaining how they were calculated if mathematicians thought them worthy of his efforts. So Napier was still alive. Robert was just kind of his press man. He was a social media guy. Robert indicated that his father died before finishing his book and that he had taken up the task of completing and publishing it. I take that back. So this social media guy was living the legacy. He's Hank Williams Jr., right? Hank died. He wants to keep the music going. It seems reasonable to add Napier's work in an appendix explaining a new kind of logarithm that he had mentioned in the introduction to his one of his books. He had also included an appendix by Henry Briggs, that comments on the new logarithms and the rules Napier's had set down for solving trigonometric problems in spherical triangles. So there was a lot of talk about this thing, whatever this thing is, the Metaphysi Logarithmoris Canonis Constructio, yeah, and the tables of artificials. Okay, so it's written in Latin, because that's what they did. All right? And we start here right away. Posito primo, we have the first proposition. So Napier's work consisted of 59 propositions, which describe everything from a logarithm table to its final construction. So have you ever really wondered what a logarithm is? We're looking right now at where they were created. Proposition 1. And I'm not going to go line for line here in the translation, but a table of logarithms, artificial numbers, is small, but with it, one can do multiplication, division, and extraction of roots, right? And what's the first thing we learn with logarithms? Product property, quotient property, and the power property, extraction of roots. Proposition 2, which continues on the next page. Proposition 2 says, progressions of numbers are two types, arithmetic and geometric. Arithmetic progressions are ones with equal intervals between entries, 1, 2, 3, 2, 4, 6, all that good stuff. While geometric progressions are those with increasing or decreasing intervals, as long as we have a constant multiplier. So 1, 2, 4, 8, 16, right, powers of 2. Or 243, 81, 27, 9, 3, 1, dividing by 3 each time. Propositions 2 through 6 on this second page here. If you start with a big number as the radius of a defining circle, your table of signs, that's right, trigonometric signs, will be more accurate than if you start with a smaller number. So it's saying, why would I use a unit circle when all of my numbers have to be between 0 and 1? When instead, I could use a large number, let's call it 10 million. If I use a large number for the radius, then as I'm constructing my tables, all of my numbers are between 0 and 10 million, not between 0 and 1. It's easier for us to work with even now, but definitely here in the 1500s, early 1600s. I guess this one's probably, early 1600s. So you can use decimal fractions to add more digits. Number 5 specifically says, describes decimal fractions, which were then quite a new concept. So this is telling you, hey, instead of writing it as a fraction, let's just write it with a decimal point. Here we see very, very new notation of something that 6, 7-year-olds are now doing, right? Decimals. So there we see it in Napier's work. Right here. All right. After calculating the table, you can remove any decimal fractional digits as the error, because if you're using a radius of 10 million, well, if you have 0.003, that doesn't really matter much, right? We could just ignore the decimal part. So now we're looking at a concept of truncation. Truncation is ignoring the decimal part. We see this as a greatest integer function. All right, propositions 7, 8, and 9. Number 7, if a number is unknowable, so like a repeating decimal, like not a repeating decimal. If a number is like square root of 2, then you can assign a lower bound, L, and an upper bound, U, and perform the operations on these bounds rather than on the number itself. So square root of 2, right? That's 1.412, blah, blah, blah. So I could do the calculations on 1.42 and on 1.41, and I know that the square root of 2 is going to be in between there somewhere. All right, so it says, don't worry that we don't know what these numbers really are. We could use upper and lower bounds on them, number 7. Number 8 says, if doing an addition with two numbers, A and B, that have lower and upper bounds appropriately, then we can combine the lower bounds, combine the upper bounds, and we can look at the I'm not going silent, I promise. And we could look at the sums. Right? Once we combine them, we could look at the lower bounds and the upper bounds and do the combinations of those. So if I have square root of 2 plus the square root of 5, I could use the lower bound for square root of 2 and the lower bound for square root of 5 and make that the lower bound of square root of 2 plus the square root of 5. Similarly for uppers, and then I do the calculations on those, and I have the answers that I'm going to need. If you're multiplying two numbers with bounds, you'll use a cross product. All right, so instead of adding the sums, you'll multiply them. He continues with propositions 10, 11, and 12. Proposition 10, a subtraction of two bounded numbers will yield a result between the sums, the differences. Proposition 11, in division, the bounds for A over B will be between A upper over B lower and A lower divided by B upper. So 10, 11, and 12, they're just talking about all these different combinations that we could have. 13, 14, 15. 13, the construction of an arithmetic series is easy. Geometrical series are not always easy. That was the whole proposition, and then he talks about why that is. And I think we can all agree that once we hit geometric series, we were all a little confused. And then we took Cal 2 and we got really confused. And then it became clear probably 3 months after you finished Cal 2. Proposition 14, to find the 10th, 100th, 1000th, etc. part of a number, simply remove the last 1, 2, 3, and so on digits. Remove digits. Proposition 15, a half, a 20th, a 200th, etc. part of a number is easily found. All right, I had a little time out there. My dogs went crazy. I forgot where I was. All right, so let's start again at proposition 15. This is a high quality video, I'm telling you. A half, 20th, 200th, etc. part of a number is easily found by removing as many least significant digits as there are zeros in the divisor, and then divide the remaining number by 2. Yeah, we're up to proposition 15, and he's lost me also. But let's keep going. Proposition 16 is where your homework assignment starts. A table, and it's actually the first table. Wrong key. There we go. Make sure I'm on laser pointer. I'm no longer on laser pointer. Give me a laser pointer. There we go. A table of 100 numbers begins with 10 million, with 7 zeros to the right of the decimal. And subsequent entries can be found by, at each stage, subtracting its 10 millionth part. So if we start with 10 million, the second entry is 10 million minus 1, which is 9,999,999. And then we'll take that number, 9,999,999, and subtract its 10 millionth part, which is 0.9999999, and so on. So we keep doing this subtraction, and they did this by hand. The entire subtraction, the entire table, they did all of that subtraction by hand, and that makes my head melt because it would suck. Look at that. They did all of these constructions, all of these subtractions, and it's just subtraction, right? How hard is subtraction? But look at all that regrouping, I guess is the term now that we would have to do. It's going to take some time. I think when I tried it on Excel, I was able to do 100 calculations in about 2 minutes. These guys, it took a little bit longer. Over here, proposition 17, tabula secunda. So the second table is generated. Much the same as the first, except there are only 6 positions to the right of the decimal point in the starting number, whereas there were 7 in proposition 16. Proposition 17, we're only going to do 50 numbers, and the last number must be as close as possible to the last entry in the first table. So this entry that we have down here at the end of the first table, that's what we want to get to in the second table, using only 50 numbers. All right, so this can be done by subtracting the 100,000th part of each entry to obtain the next. The last line on this page says that the final entry in the second table should be, let me read the numbers correctly, 9,995,001.222927, and it's incorrect. But it's incorrect in the third decimal place. All right, over here. That's pretty impressive accuracy in doing all those calculations by hand, and to be that close at the end, pretty impressive. But we'll be better. We'll actually have the correct value. McDonald, I don't remember his first name. Later mathematician found that correction, found that error, and made note of it for his translation. Proposition 18. This is the third table. Our third table has 69 columns. My favorite movie is Bill and Ted's Excellent Adventure, and so I must say 69, dudes. I apologize. No, I don't. Each column contains 21 entries constructed much like those in the first and second tables. The first column begins with 10 billion with 5 digits to the right of the decimal point, and subsequent numbers are found by subtracting the 2,000th of the previous entry as shown. So here we have 10 billion, and I subtract a 2,000th of that. Find the answer. Subtract 2,000th of that. Find the answer. Subtract 2,000th, and so on, and so on, and so on. 69 different terms. Once the last entry has been found, it should be recorded, but then, in subsequent steps, you may disregard any of the least significant digits so your calculations will be easier. So once you get down to this number, screw the decimals, is really what they say. And so we find that the error he made in the second table really is insignificant because he used the radius that was so much larger than 1. These become just incidental numbers that we can ignore. It goes on, proposition 19. The first and last entries in column 1 are 10 million and 9,900,473, and the ratio between them is super close to 100 to 99. So we use this ratio, starting at the first column, to fill in the first entry of each column from 2 to 69. So you're going to have 69 columns. This was just the first column of the third table. Right? You're going to have 69 columns like this. They did this by hand. crazy. And so we're going to, since we're using just 100, we're going to go 1/100th. We're going to subtract 100th of the previous number each time. All right, so tables forever. And then we start getting into over here in propositions 21. This is where instead of artificial, they have a footnote, although it's not on the foot. It's a spine note. It's probably near the spine of the book. It's calling them a logarithm instead of the artificial tables. Right? Instead of being artificial numbers, they are now a logarithm, and they make that note. And now we start seeing this ratio idea. Proposition 27, and you could read through these. I'm going to provide the notes that I'm using for this lecture along with the video. Proposition 27 down here says the logarithm of the whole sine is 0. So it's telling us the log of a sine is 0. All right. 28. The logarithm of a sine will always be bounded by an upper and lower limit, which can be determined by the geometry of these lines and points. 31 and 32. Proposition 32 in a table of logarithms. If the first one in the table after the radius itself is known, then the others may be found from it simply because they will be part of a uniformly increasing arithmetic sequence. If the second logarithm in the table is x, then the third will be 2x, the next 3x, and so on. And of course, that's with our notations. He's not going to be using the variable form because they didn't really do that yet. More propositions, more Latin that I can't necessarily read. What do we have here? 36. Similar proportions give, it looks like equal different artificials. So that says if signs are in the same ratio, for example, a over b and c over d are the same, then the logarithms of a and b and the logarithms of c and d are the same when subtracted. All right, so here we get our quotient property. All right, the quotient property of logarithms comes to us here in proposition 36. Uh-oh. Looks like somebody got a little down on their tech here as I made this slide. What do we have? 38, 39, 40. Propositions 39 and 40 show that the difference between the logarithms of two sines lies between a lower and upper limit, and these limits can be so close that their difference can be ignored, thus giving you the logarithm of the difference between two logarithms of sines. Simply is to say that if you know the logarithm of two sines, say a and b, you could easily find the logarithm of a over b. The exact process, how to do that, we could see it in the translation, even if we don't necessarily find it in the work of Napier here. Oh, I see what I did. Interesting. Okay, 41. Proposition 41 instructs the user that should they want to find a logarithm of a sine, he used the word sine, natural number, that's all a sine is. Natural numbers, sine, think about what a sine is. Sine is a ratio. Natural numbers are a ratio with the denominator of 1. If you want to find the logarithm of a number not in the tables, you can use the process of the last few propositions to determine the value. So if it's not in a table, you can find it, which is hilarious because, no, we probably couldn't at that time. But it's funny how from early 1600s, even through 1950, so we're talking 350 years, once this was constructed and they found all these tables, the same tables I'm having you construct, I have books in my home library of just logarithms, just tables and tables of logarithms. People printed these for centuries because nobody wanted to have to calculate it again. And here we sit, phone in our pocket, we could easily pop up, let's find a log of any base. It didn't even have to be base 10. This is all base 10. We could find the log of any base quicker than they could pull out a pen to write on whatever paper they had around at the time. Propositions 44 and 45. Let's get to them. Where are we? Oh, there's 44. I'm going to back up. Proposition 43 provides an example of the process. So here's an example of what you would do in order to calculate a logarithm. Kind of cool, actually. 44 and 45 show that logarithms for numbers not actually listed in the third table may be determined by following the process similar to those for earlier tables. And it just keeps going and going and going. Excuse me. Yeah, I should have paused the mic on that one too. So let's talk about something, what we might do here. If we double, if we quadruple, if we notice 2, 4, 8, decupla. Interesting. Notice how the proportional values, I'm learning some new words over here in Latin. Proposition 54 at the very bottom. If a number falls outside the limits of a radical table, then multiply it by 2, 4, 8, 10, 12, or whatever, until it falls within the limits of the radical table numbers. Select the logarithm of the resulting number, or the nearest one to it, from the radical table and add the logarithm from the table, so columns 2 and 4. So it's telling you, once you have these tables constructed, you can now find the logarithm of any number out there just by using the tables. So glad we don't have to do this anymore. Propositions 55, 56, and 57 provide some trigonometric identities that can help simplify the calculations to find a logarithm of certain numbers. What is that? That is a failure to operate PowerPoint correctly. Let's just get that one down there too. 52, 58. Where are we? I can read. That looked like a 52 over here. 58, once the logarithm of numbers greater than 45 degrees are known, then ones less than 45 are easy to find. Using proposition 57, it's possible to find all the logarithms for numbers down to 22 degrees, 30 minutes, and from these down to 11 degrees, 15 minutes. In proposition 59, the last of the propositions, Napier describes the layout of the tables in his Descriptio. So this is an attachment in an appendix. It references an appendix in another book. And here we have, at the end, after finishing his 59 propositions, Napier, wow. I don't know how I screwed this up so bad, guys. We'll just go with it. After finishing his 59 propositions, Napier pointed out that because there are two different processes that could be used, propositions 54 and 58, to calculate a logarithm, they might differ slightly, and in fact they do. He suggests that if you start with a table of numbers that are more accurate than his, and he's thinking 100 billion as your starting number instead of 10 million, the problem will be eliminated. So you want better accuracy, use a larger radius to start. Now this appendix, in which Napier describes his base 10 logarithms that were developed by he and Henry Briggs. In this case, base 10 system that he proposes, log of 1 equals 0, log of 10 equals 10 million. Once again, and remember now, right, we know that the common log base 10 of 10 is 1. But he said log of 10 should be 10 million because that's where the first table starts. It starts at 10 million, right? We expanded our radius of 1 to 10 million. Once again, the English translation by MacDonald, mentioned earlier, is a great one to go to if you want the actual translation. I used all of these images. They're courtesy of Erwin Thomas and the Thomas Library on the History of Computing, copyright 2009. You could probably find it just with that information. This lecture was important for two reasons. One, you guys really should hear my voice at some point. Two, you're going to be doing a project very similar to this where you're going to be using original sources. Once our timelines are finished, I want you looking into the original writings of mathematicians and seeing if you could translate. Like be that math historian that just kind of reads the actual works of some of these great people that we've learned our techniques from. All right, so that's it for this particular lecture. I'm going to do a second one that's just showing you kind of how to start the first table, second table, and a third table, possibly. I'll at least get them started, and then you'll have some more work to do from there. All right, thanks for listening, guys.